Welcome back, everyone. Today we're diving into a real scientific detective story in this explainer. We're going to explore exactly how humanity figured out the invisible building blocks of our entire universe. We'll be looking at some of the most ingenious experiments in history to trace how the atomic model actually evolved over time.
Okay, let's dive into this. Here's our roadmap for today. We're starting with unlocking the atom, then discovering the electron, followed by measuring the electron. From there, we'll hit the gold foil experiment and wrap up with the modern nuclear model. Let's get to it.
Section 1. Unlocking the atom.
Now, for a really long time, the nature of matter was just this profound mystery. Back in the early 1800s, John Dalton proposed that atoms were literally the smallest possible pieces of matter. The idea was that the atom was completely indivisible, just this solid, unchangeable sphere that you couldn't break down any further. But, as you'll see, that simple assumption was about to be seriously challenged.
Section 2. Discovering the electron.
So, fast forward to the laboratories of the late 1800s. Scientists were playing around with electricity in vacuums. And that supposedly indivisible atom, well, it started to break apart right before their eyes. English physicist J.J. Thomson was working with a cathode ray tube where a visible beam was produced inside a glass vacuum. To figure out what this beam actually was, magnetic and electric fields were manipulated around the tube, and the results were incredible. The beam was deflected by a magnet, and it was drawn right toward a positive electrical plate. Since opposite charges attract, Thomson knew for sure these mysterious particles had to be negatively charged.
Based on exactly how much that beam bent, Thomson realized these particles were tiny. He had just discovered the electron. This was an absolute game changer because it proved atoms actually have a substructure. They aren't just solid spheres, they're made of pieces much, much smaller and lighter than the atom itself.
Section 3. Measuring the electron.
Now, what's really interesting about this next part is, how do you weigh something you literally can't see? That brings us to Robert Millikan's brilliant setup in 1909. In his experiment, microscopic oil droplets were sprayed into a chamber. As they fell, they naturally picked up a negative charge. Then, their downward fall was slowed down and even totally suspended in midair by an electric field applied to the plates. By carefully tweaking that field, the fundamental charge of a single electron was successfully measured.
And that measurement gave us this unimaginably tiny number. Because Thomson had already figured out the ratio of the electron's charge to its mass, once Millikan found the exact charge, scientists could easily calculate the mass. They confirmed that the electron is an extremely light particle, proving beyond a shadow of a doubt that something way smaller than the atom actually existed.
Section 4. The gold foil experiment.
Okay, so we have these tiny negative electrons. But atoms themselves are electrically neutral. That means there has to be a positive charge hiding somewhere inside to balance the whole shebang out. Thomson thought he had the answer with his plum pudding model. He pictured the atom as this uniform sphere of positive charge, with the tiny negative electrons scattered inside it, kind of like raisins in an English pudding, or chocolate chips in a cookie. It made perfect sense at the time.
But Ernest Rutherford wasn't just going to guess. He wanted to rigorously test it. In 1910, extremely fast, positively charged alpha particles were fired at a very thin piece of gold foil. The thinking was, if the plum pudding model was right, the positive charge in the gold atoms would be spread out so incredibly thin that those heavy, fast alpha particles would punch right through with basically zero deflection.
Well, the results were absolutely shocking. Most of the particles did pass right through, but a few of them actually bounced back. Rutherford's mind was completely blown. I mean, as he put it, it was as if you fired a massive 15-inch artillery shell at a piece of tissue paper and it ricocheted right back at your face. That is how utterly impossible this seemed, based on everything they thought they knew. So, what on earth actually happened? Because most particles went straight through, the atom had to be mostly empty space. But occasionally, alpha particles were scattered at massive angles, and that could only happen if they smashed into something highly concentrated. The positive charge wasn't some soft, diffuse pudding after all. It was a microscopic, incredibly dense core.
Section 5. The modern nuclear model. So, the crucial point is that Rutherford's gold foil experiment completely shattered the plum pudding model and gave birth to our modern view. He concluded that the nucleus is the absolute densest part of the atom. It is the smallest, heaviest, and most tightly packed region imaginable. To really put that scale into perspective, if the nucleus were a blueberry sitting right on the 50-yard line, the atom's empty space where the electrons live would be the size of the entire surrounding football stadium.
Over the next few decades, scientists nailed down exactly what's inside that nucleus. We now know the electron is much lighter than the proton. In fact, it takes over 1,800 electrons just to equal the mass of a single proton. Meanwhile, the neutron, which has zero charge, is slightly more massive than the proton.
To summarize this beautiful architecture, those tiny, incredibly light electrons are just zipping around in a vast volume of empty space, and their interactions dictate all of chemistry. Deep inside, the number of protons defines exactly what element the atom is, and those neutrons act as a sort of glue, adding mass and creating different isotopes of the same element.
But before we go, I want to leave you with a thought that should kind of bother you. We know for a fact that like charges strongly repel each other, right? So, if you pack a bunch of positive protons together into the absolute densest, tightest space imaginable, what incredibly powerful force is stopping that totally positive nucleus from violently blasting itself apart? Well, that mystery is exactly what we will unpack in our next explainer on nuclear chemistry. Thanks for learning with me today, and I'll catch you next time.